Now that we've studied e and log, we can use those functions to model various situations. This video discusses a growth model. Here's an example. The size of a bacteria sample doubles every 6 hours. If there are 16 bacteria to start, how many are there after 2 days? So how many are there at 48 hours? When are there going to be 1,000,000 bacteria? So when are there 1,000,000 or 10 to the 6th bacteria? So to solve this problem, what we're going to do is the following. I'm going to let f of t be the number of bacteria at hour t. So this sentence says if there are 16 bacteria to start, can be interpreted as f of 0 is 16. I'm going to model this situation since the bacteria sample is doubling with the following function. We're going to say that f of t has the form 2 to the at plus b power. So what I'm doing is I'm taking the function 2 to the t. Reason I'm starting with that is because the bacteria sample is doubling, so it seems like it's going to be some power of 2. And I'm scaling and shifting it, so instead of 2 to the t power, I have 2 to the at plus b. So that's scaling and shifting the function. Here, a and b are some constants that I have to find out. Once I know a and b, I can answer the questions about this situation. So we know that if I plug in 0 in for t, I get 16. If I plug in 0 into this model, I get 2 to the b power. 16 happens to be 2 to the 4th power, so I know b has to equal 4. If I didn't have that observation, I could take logarithms on both sides and solve that way. But here I see b has to equal 4. I know that the sample size doubles every 6 hours. So after 6 hours, if I have hour 6 in here, I should get 32. So if I plug in 6 for t into my model, I get 2 a times 6 plus b, which I already identified as 4. Now 32 happens to be 2 times 16, so it's 2 to the 5th power. So 32 is actually 2 to the 5th power. So I know that a times 6 plus 4 should equal 5. If you didn't see that, again, you could take logarithms on both sides and simplify. This gives you, subtracting 4 is a times 6 is 1, so a has to be 1/6. Therefore, I know my function f of t at this point is 2 times t divided by 6, so t divided by 6, plus 4. Now I can use this function to answer the questions. At 48 hours, the function is f of 48, and you can plug that in here. So I get 2 to the 48 divided by 6 plus 4. And if you do the arithmetic, I believe you get 4,096. So after 2 days, there are 4,000 bacteria, starting from only 16. As we've been discussing repeatedly, exponential growth is extreme. It grows very fast. To find the answer of when there are 1 million, we want f of t, which we now know is 2t over 6 plus 4 to equal 10 to the 6th. I can now solve taking logarithms. So taking the natural log on both sides, I get natural log of 2 t over 6 plus 4 should be natural log of 1 million. The reason I took natural log on both sides is because of the properties of natural log. This allows me to pull the exponent in front. That's one of the key properties of log. So I get t over 6 plus 4 times log 2 is equal to log 1 million. Now, I could simply solve for t. Everything here is a constant except t. So log 2 is a constant, 4 is a constant, 6 is a constant, log 1 million is a constant. Sometimes I've seen students get tripped up at this point because they have log 2 and they kind of freak out a little bit because they're not super comfortable with log. Just remember, this is a number. So you can solve, and if you solve, you find t, which is about 95.54. That's in hours. If you translate to days, that's 3.98 days. So 4 days. I'd like to end this video by changing the assumption a little bit that our model looked like 2 to a power. What if you didn't guess that? How did I come up with this? Well, let's suppose now that instead of 2 to a power, maybe I guessed differently, and maybe my function looked like e to some exponent like at plus b. How would things change if instead of 2, I put an e here? Notice, before I continue with this line of reasoning, properties of exponents allow me to write this as e to the at power times e to the b. Now, t is a variable, but a and b are constants that I have yet to find. E to the b, therefore, is a constant. And some people like to call this another constant, c, so our model really looks like c times e to the at. So I'm going to use this model instead of my previous one and see what's different. Now here, what we have is that f of 0 is 6. So if I plug in 0 in for t here, I get c times e to the 0 power. E to the 0 power is 1. So I just get c times 1. Therefore, c is equal to 6. Now I also know that f of 6 hours is 32. So I know that 32 should equal, when I plug in t equals 6. Now I know c is, c was 16. It started off with 16 bacteria. So 32 is 16 times e to the a times 6. You can divide both sides by 16. You get 2 is equal to e to the a times 6. If you apply the natural log to both sides, you get natural log 2 is a times 6. So a is natural log 2 over 6. Now that I know c and a, watch this. So now what we have is that my function, f of t, is 16. E to the AT, where A is this, so e to the t divided by 6 times log 2. That's my model. However, I could use properties of log to make this look a little bit different. I can take this log 2 and write it as log 2 to the t over 6 power. E and log are inverses, so when I compose them one after the other, they cancel out, and I get 16 times 2 t divided by 6. And to finish things up here, I'm just going to remark that 16 is 2 to the 4th, so this really is the same exact model that I had before. So it actually really doesn't matter the form of the model as long as it's an exponential function. You'll always be getting the same answer out in the end. Okay, nice.